We'll get started with Greg Clifford from Cray, HPC Environments for leading edge simulations. Welcome.
Well, good morning. I appreciate everyone coming to the talk. Hopefully everyone can hear me okay with the mic. So my name is Greg Clifford. I am the manufacturing segment manager for Cray. And I must say I'm a little bit out of place in the PBS talk here, I think, since my background is much more in the simulation codes and analysis section. But I put together the title for the talk, HPC Environments for leading edge simulations a while ago. And I must say my presentation will probably actually vary a little bit from that. So I decided to kind of go with three main topics. And the first one is, since we get this a lot, at conferences like this, is, hey, so what's Cray doing now, right? So I wanted to start off with a little bit of where Cray is at, what our products are, and just where we are in the marketplace. And the second one is, the second major topic is to kind of adapt a presentation I gave a while back on, focused basically on, what is the scalability of application codes now, especially ISV application codes in the CAE space. So again, that's another thing we get all the time is, so just, how scalable are these application codes? And just, how that applies and how I think that's going to impact the marketplace moving forward. So, by the way, if you do have any questions, I guess the format has been to take questions at the end, but feel free to interrupt me as we move forward. It actually makes it a lot easier for me to have a little more of an interactive discussion. So, if you want to do me a favor, you can ask me a question. Okay, so first of all, where is Cray at? I think everyone is familiar with the Cray brand. Obviously, it's synonymous with high-end systems and supercomputing in general. And indeed, that's where still the bulk of our business is in the computational space and building large computational systems. And I'll give a little more background on that. More recently, we've also have developed an explicit storage part of our business. This is built around Lustre and specifically Lustre appliances. So obviously, virtually every computational system we sell has a big component of storage attached to that. The third one is in the whole area of big data and data analytics. This is a very special purpose product we call Eureka. It has a relatively unique architecture that's really well suited for graph analytics. So part of the message at Cray is, of course, computation is what we've known for, but big data, with our storage solution and data analytics is, kind of helping to tie all this together. And one of the things I've been listening for here, actually, in the presentations this week, is just, how big data is impacting people's business and simulation environment right now. So that's something I would welcome to talk to people about. But we've had a lot of success, as I'll show you, at the high-end systems. More and more now we're pushing down into the manufacturing segment, the petroleum industry, energy industry, life sciences, financial services. So taking our products across that whole broad range. And as I mentioned, my focus is right here in manufacturing. And as you'll see in my presentation, I kind of have a manufacturing bias to what I'm presenting. In terms of our computational solutions, we've got two main products. The first one is our Cray XC30, which is sort of our legacy business, or our mainstream business, I guess, for lack of a better term. It's basically a cluster solution built on Intel processors with each node having 2 sockets. The main difference between the XC30 and the other part of our business, which is the Cluster Solution 300, CS300, is that most of these systems are built around an InfiniBand interconnect, whereas our XC30 is built around the Cray proprietary interconnect. So these systems are designed and built to scale up to very, very large systems and be able to scale your application across that entire system. And as you'll see, we have many customers scaling up to hundreds of thousands of cores on single simulation runs. The CS300, again, sort of high performance computing focused, but since it's built on more standard components, it allows more flexibility in the architecture and the environments it would fit into. Okay, so what's Cray been doing for the last 10 or 15 or 10 or I say 5 or 10 years is probably more accurate. when the vector computers kind of went away, and that was about 10 or 15 years ago now, and the marketplace shifted to distributed parallel systems, Cray's products shifted to massively parallel, very highly scalable systems. And we've been very, very successful in selling these systems to a lot of the big research labs and university centers and that sort of thing. So a few notable machines, I guess, on this list. This lists some of our larger systems. The PF stands for petaflop scale. So think hundreds of thousands of cores in the system. Probably the one that's been one of our showcase sites for a long time is at Oak Ridge National Labs. It's currently called the Triton system. It was recently upgraded. Prior to that, it was known as Jaguar. Again, I don't know the exact number, something like 200,000 cores in that machine. This is actually a hybrid system with x86 processors and GPUs and a GPU on every node. Another real notable system is the one at Blue Waters. This is physically the largest system we've ever built. I think it's 300 cabinets, and people run, as you'll see, simulations across all 300 of those cabinets. So a few other ones I'll point out. Hector was the largest machine. It's in the UK. It's the largest machine in the UK at the UK Supercomputer Center. HLRS is in Stuttgart. Again, a resource for the Stuttgart area. And you can see as you go around here, these are the DoD machines, National Labs, Los Alamos, and so on. So again, at these high-end research centers, Cray's been very, very successful. So one of the things that we've seen, and one of my messages in this talk is, Cray's business are these highly scalable, very large systems. And what we've seen in manufacturing space in particular is that more and more people are starting to push the limits of their simulations and not just go 32-way parallel, which is one node now, right? Or basically or a couple nodes. They're starting to go to more, 128, 512, 2,000-way parallel. So as Cray's product has become more, general purpose, it's the same time that workload is pushing up. So now we're seeing much more of an overlap between Cray's value in what we bring in our systems and what the workload in the marketplace is. Well, here's a couple examples. This is the NERSC machine. This is an example of our, previously this was called Hopper with our previous generation. They've just upgraded now to Edison, which is our XC30 machine. And this is a couple of, is actually a snapshot taken from their queues. And what it shows is a couple of examples. This is a geoscience simulation. The reason I put these up is just to show the kind of workload we see on the systems. So this particular simulation is using 65,000 cores, all one simulation. And total core hours is over 200,000 core hours for that simulation. So that's the sweet spot for Cray machines. How many people are running 65,000 cores in their simulation today? I'm not expecting anyone to raise their hand. But another example is a nuclear physics simulation. This was actually done on Hopper, which is the previous generation. 28,000 cores, 33,000 core hours. And this is another really big example of a WRF simulation. WRF is a weather forecasting code, if you're familiar with that. And it shows the previous simulation that was done 3 kilometers. So that's basically the grid size for doing weather forecasting. And they went from the 3 kilometer fidelity to 500 meters. So 6 times more fidelity per section, or per line. So that's 6 by 6. You're getting 36 additional cells in the grid, 36 times more. And the point is that with this increased fidelity, they're able to see much more accuracy. This was actually a simulation of the Hurricane Sandy. And I'm not a weather forecasting guy, but the guy was pointing out to me of all the additional detail they're able to see up here in some of these weather bands. But for me, what was cool about this is that simulation scaled all the way up to, you probably can't read that number, but 400,000 cores, one single simulation. So that's, again, what kind of the Cray systems are all about. And my job is to take that scalability and find the value for that in the manufacturing sector. So first question is, well, we don't run core, CAE jobs don't use 100,000 cores at a time. And one of the things I wanted to point out is, indeed, we do see CAE simulations on a lot of our centers. A lot of the DoD sites run them. The machine in Stuttgart is supporting the automotive industry there. And here's an example of a 1 billion cell CFD simulation of an unmanned vehicle in, and you can see it's, again, probably a little hard for you to read, but the number of processing cores, you can see it's scaling up to 20,000 cores, actually scaling to 24,000 cores in the simulation. So, CAE algorithms really do scale up that high. Here's the CTH code. My guess is some of you are familiar with the CTH code and maybe even have that running in your centers. This is a Shock Physics code, very widely used in the DoD area. And talking to one of the developers, he says CTH will scale to 10,000 cores, no problem. And a single user doing a parametric study can consume all of the Jaguar system, which again is in the order of 200,000 cores. So there is workload out there that in the CAE area that can demand this kind of performance. And this is from a totally different field, but it kind of addresses the topic of what's the business case for in the commercial marketplace for machines of this size. This is actually from the seismic processing area, also an important part of the PBS world. And this shows basically the years going by here in time versus the amount of compute power to do the state-of-the-art algorithm that they want to do for seismic processing. So one of the trends in seismic processing right now is to go to the full wave field inversion technology, FWI, and to do that, which is the next step in accuracy over the RTM method, that's a petaflop class system. So a petaflop class system is what they typically have at the large labs right now. And what we're seeing is the petroleum industry is putting their money where their business is, so to speak. And we do have one of our largest systems that went in last year was into the petroleum industry specifically to support the seismic processing area. So we're starting to see this class machine move into the commercial marketplace. And the other key thing, though, is that it makes sense. You got to have that value proposition. The guy who presented this morning from Honeywell, I thought it was a really good point he made that all the components that have to go into introducing introduce this new technology into the environment, and one of them was you got to have the value proposition to justify it. Okay, so getting a little closer to home here in the CAE space, this is a chart. It's a pretty basic chart, really. It's basically showing the combination of what's driving up the requirements for compute intensity, and of course the fidelity of the simulation, the size of the models, and so on is one trend, and the other one is the move towards more ensemble type analysis with design of experiments and robust design type simulations. And of course these things are not mutually exclusive. They tend to couple together, and very quickly you get to environments with thousands of cores. And I put this slide together about 6 months ago, actually, maybe 9 months ago. And I thought, a couple thousand cores, that's certainly in Cray's sweet spot. And there's a lot of environments out there now that have a couple thousand cores. Well, probably more accurate to say is there's a lot of environments out there right now that have 10,000 cores. And 50,000 cores, certainly for large automotive organizations, is pretty common. So just in general, the CAE space it reflects, I think, that trend that Cray systems and what we're architected for is becoming much better fit for manufacturing sector. And I really like this quote that one of the CAE developers said is that simulations allow engineers to know, not guess, but only if IT can deliver dramatically scaled up infrastructure, and that means thousands of cores per mega simulation. I like that quote because that's kind of the Cray message, right? And that's something we're hearing not only from the ISVs, from Altair and other spaces, but also from more and more from customers that we want to be able to run simulations that scale across not 1,000 cores, but 10,000 cores. Okay, so part of what we hear is, well, that's all great, and yeah, we'd like to run 1,000 cores, but ISV codes don't scale. So, you know, what's the reality of that? And this kind of gets into that other talk I put together. And this is a rough cut at what is the workload out there in the manufacturing space in general. And, you know, my take on it is it's probably looking across automotive, aerospace, everything. It's probably about 40%, you know, impact simulation or crash type codes. Radius, for example. Maybe 30% CFD, you know, AccuSolve and from Altair is a good example. And then the structures, you know, OptiStruct or whatever it might be. I also included electromagnetics. I think that's a very important space. Little harder for me to measure, to be quite frank, because a lot of that electromagnetic stuff is classified, and it's harder for me to get a sense of what's going on there, but it kind of gives you a flavor for this. One of the points I'm putting this together is CFD, crash simulation, electromagnetics, all of that is all standard running now MPI parallel. So these codes do run across a distributed computing environment. The structure stuff, I would say, has MPI capability, but it's probably not common to see that, you know, scaling to more than a dozen cores or something like that. Well, okay, so here's my sort of sense of the status of things. So first of all, you know, ISV codes dominate the workload right now in a CAE environment, and many large manufacturing companies have well over 10,000 cores. I was at what I would call a medium-sized automotive company a couple weeks ago, and they had 10,000 cores in their environment. I mean, they were a subsidiary of the larger company, right? Sort of like a satellite site. They had 10,000 cores in their compute environment. But even for these large organizations, it's relatively few jobs are run at more than 256 ranks, MPI ranks, or 256 cores at a time. So there's this huge discrepancy, I think, in terms of the capability of the application codes, which scale to thousands of cores, and the amount of compute power available, and what's being used out there. So, you know, the question is, you know, why aren't more commercial CAE environments leveraging, you know, scaling better? I'd welcome others' perspectives on this, but I'll give you my couple thoughts here. So this is the image, and I guess it's one of my key points of the presentation is, you know, the full power of the environment is really not being leveraged. So I don't know how that picture's showing up, but that's looks like some kind of Ferrari or something, and a European picture, a little Traube or whatever that is, trying to passing him up on the highway. And I thought that kind of captured this. You know, people are running 64. I mean, the simulation you're doing is critical to the design process. You're running 64-way parallel, and the capability is there for you to run literally 6,000-way parallel. I mean, I can live with the factor of 2, but we're off by 2 orders of magnitude. So, you know, that's something, the message I want to send is I think there's tremendous potential to ramp that up. Okay, so part of this is just showing, is there a case algorithmically to make that happen? And I thought this slide was worth throwing in. This came from the PRACE project over in Europe. It was presented at the ISC conference last June. And it shows sort of really more of a gas turbine engine thing, but different algorithms and capabilities. So it's kind of similar to that seismic processing chart that I showed earlier. But, and again, it shows as you start getting up here into the 2013 range, you're approaching, petaflop scale compute requirements to do the latest algorithms. But one of the things I liked about this chart is it talked about the time it takes algorithmically for this technology to make it into industry. And if you can pick it up there on the chart, it's about 5 years. From this paper, they said it takes about 5 years from the time these algorithms are being done in the research environments until they're into production environments. And one of the reasons I thought that was interesting is I did kind of a similar thought or review of, if you look at how long did it take for vector processing to go from Los Alamos National Labs, where it was first introduced, or was it Livermore? Anyways, the labs, to make it into the automotive industry. And if you look back, it took about 5 years, and really it was Nastran code that really drove these initial installations. And then if you look at, okay, how about parallel processing? Well, it started with, at least from the Cray perspective, with the XMP, and eventually became commonplace in, again, in automotive and aerospace, really in the YMP technology, so about 5 years. I talk about sort of, MPI parallel simulations. You started seeing this in a lot of the more research type environments in the late 90s, and it really wasn't until early 2000 timeframe we started seeing again in automotive. These are, Linux cluster-based technology. So my next step is what I refer to as extreme scalability, right? Not scaling to 64-way parallel, but scaling to, 640-way parallel. This is, as I showed, very common right now, and certainly in the Cray environment. And I think we're due to start having this start making its way into production in automotive environments. And one of my questions is, what's going to be that application that drives this session? Because if you look back at all these other introductions of technology, there was some kind of application that typically drove that, whether it be crash simulation, more crash and CFD here with MPI parallel. From my perspective, most likely it's going to be in the computational fluid dynamics area. That's where there's the best fit right now. That's where the codes really scale up. Okay, so why hasn't this been happening more? And so here's my take on it. Well, to start with, and this is really kind of a PBS statement, is most CAE environments really aren't configured, or are configured for capacity computing. So it gets, when you're running hundreds of 64-way parallel jobs, it's tough to schedule a 1,000 core job into that type of environment. And because of that, people tend to build their models and their compute problems. They typically want overnight turnaround, so they kind of make their problem big enough to fit in, whatever environment you're going to be able to run in. My personal feeling on that is that as compute environments are changing and you get tens of thousands of cores in the environment and scheduling capability becomes better, that's going to evolve, and it's going to take care of itself here as we move forward. Another big issue is application license fees. You hear this all the time. We can't buy more hardware because we can't afford the license cost. And obviously that's an issue. But again, we see the ISVs really working to address that. And it's probably a touchy thing for the hardware vendor to be talking about. But that's acknowledged as a problem, and the pricing models are really adjusting for that. And also, Cray can't do much about it. But the third thing is, application codes really have to have end-to-end scalability. So it's not good enough to take some test case with no complexity in the model whatsoever and scale it to 2,000 cores, because that's not the real world. You have to have, if it's crash simulation, the contact algorithm has to scale, the airbag algorithm has to scale. All of these features have to scale to really take advantage of that. And this is an area where Cray is trying to work with our ISV partners and improve that. So this is a very active area, certainly at Altair. These next few slides are from a webinar that Cray and Altair put on, maybe 3 months ago now. And it highlights some work around the AccuSolve code coming out in version 12. And basically, they incorporated some Cray libraries. We did some profiling of the code with them and did a lot of testing on both our XE6 and XE30 environment. And what you see here is, and this is kind of a key example, is in the previous version, version 1.8, you can see the scaling starts to bend off here at something that's 150 cores right there. You probably can't read the numbers. But in version 12, you can see pretty much linear scaling all the way up to 250 cores, roughly, which is significantly better. But I think there's still room to go for improvement beyond that. This was a relatively small model. 1 million node is actually not quite trivial, but approaching that these days. But they did another they're looking at larger problems, 1 billion elements. But this is actually one. So they did 2 examples here. One with a 70 million element, automotive, external aerodynamics, and then a 140 million elements, internal flows in the passenger compartment. And this is kind of a busy chart, so forgive me, but it summed it up all on one slide, and I thought that was good enough. So the red is the 140 million element internal flows problem. This is on Sandy Bridge on our XC30. The green is 70 million elements, also on Sandy Bridge. The blue line is not that important. This is our older technology. And this dark simulation, which really doesn't even show up because we didn't have many nodes to compare to, is down there at about, is a Linux cluster simulation with Sandy Bridge. So you can see that it's actually quite good scalability, especially for the larger model, 140 million cells up to, that's 1,000 cores right there. And out here at the end, which I think is still very acceptable scalability in a production environment, is up at 2,000 cores. So, and one of the things I thought was interesting is you can see what, and this is basically an Altair slide, but down here from 0 to 600 cores, you can see that yellow box, and that's labeled small core counts. So that's part of the message I'd like to have to get out to industry is 600 cores is small core counts. There's tremendous potential beyond that we really want to try to get to. And this was from the webinar conclusion. So it talks about basically just the XC30 was showing much better scalability. And one of the questions that comes up, I probably should have touched upon this earlier, is so the XC30 and the InfiniBand, they're very similar architectures. When would you propose one versus the other? Well, if you only want to scale to 256-way parallel, the InfiniBand clusters, our CS300 product, is probably going to be a very good fit for you. If you want to scale to 6,000-way parallel, I'm pretty sure it's the XC30 that's going to be the better solution. If you want to scale to 600-way parallel, then we need to probably talk about it more because it gets to be kind of the gray area. What's your workload? Where do you see yourself going? And it takes a little more discussion to figure out what's the best fit. So, okay. In summary, I guess I'm close to being on time. Extreme fidelity simulations are really going to require a significant amount of HPC performance. And right now, with the direction of processor technology, extreme scalability is the only way to get that level of performance. GPUs are an interesting topic, but maybe for a certain segment of the market, they'll help. But at the end of the day, you need to scale to hundreds of thousands of cores if you want to get to that level of performance. And Cray systems, that's what we're designed for. Large production HPC environments. So whether it's a single job running 10,000 cores or 100 simulations, each using 100 cores, I've been talking about scalability of individual problems, but really Cray is all about big installations. So that's our focus. The technology is really in place to scale to many thousands of cores. So it's part of, I guess this is the key message, is that I think we're way overdue to see a huge ramp up in the number of cores being used. And again, I'm already seeing some signs of this, but I think there's a long ways to go. So running your crash simulations, not 32-way parallel, but 320-way parallel is ready to go right now as far as I'm concerned. So instead of waiting, I don't know what the right number to throw out here is, but 30 hours for a simulation, you can get it back same day, multiple jobs in the same day. So, okay, that's my end. I borrowed the Altair slide for my questions, but thank you.
For a couple of questions.
Yeah, I kind of have an observation. One of the things that we find is because our systems are so busy, users are tuning their job sizes down to get turnaround. One of the things that we had back on our Cray X1 and previous systems is checkpoint restart. I think probably the key to being able to use to get these large-scale jobs in a busy production environment is an effective way to do preemption.
Yeah.
And so I'll take comments from either of you guys.
Yeah, so the idea of, let's say you've got 3,000 cores in the job, it's grinding away, and it gets to be 8 o'clock in the morning, and suddenly you're flooded with hundreds of 30 core jobs. Yeah, so that capability exists, whether it's in the application or PBS Pro or whatever it might be, to take that, basically suspend or preempt that 3,000 core job, kind of set it aside until the system quiets down at night or whatever, and restart it. So that capability is there. It's not my personal area of expertise, but yes, we hear that from many places, and indeed that's one of the reasons it's been implemented. Actually, in the weather forecasting area, that's really a very, very important criteria and something that's been implemented there.
Well, we're doing a lot of suspend resume work these days,
Yeah.
and actually sort of in conjunction also. But I don't know which part's roadmap and which part's done, so
Yeah.
I don't want to say any more. Other questions?
Again, I'm speaking from a business side here. When you have these kinds of simulations that kind of ramp up and consume 6,000 cores for a couple of days, and then the analyst or the engineer has to deal with the data, that takes a few days to
Yep.
digest all the data, then you really don't have a lot of usage, and then you take it to your management, for example, and say, well, the machine's idle for 40% of the time. Is really not the true picture, right? And when you really need it, the capacity. So that's one of the things I found it difficult in looking at the usage, and that's where PBS comes to work. But if all your workload is this type of 6,000 core job that run for a certain amount of time, and suddenly the machine ramps all the way down to. So
yeah,
I don't know if there's an answer, but just a comment here.
Yeah, I think
then
it's a
dealing
good point.
The other part of the equation is the data, dealing with data and digesting the data from these simulations.
So actually, I had another slide which I yanked out of my presentation here. So what are the pros and cons of running these really big simulations? And I'm not proposing that everyone suddenly start, only jobs you run are fill up the whole machine and they kind of stack up one after another, because from a practical standpoint it doesn't work. But I think in the work environment, if you've got a 10,000 core environment, which my guess is you guys are moving to if you're not already there, yeah, maybe the max job size is 1,000 cores or something like that, and then maybe you have a whole bunch of jobs at more like 250 cores, and it'll be more of an aggregate type, mix of simulations. But what I see now is, people have 10,000 cores and their maximum job size is 256, so they're very focused on just filling it up with lots of smaller jobs. And needless to say, there are many advantages to running big jobs. Obviously faster turnaround, but engineers aren't sitting around waiting as long. If they make a mistake, the job doesn't sit there for 3 days and they find out, oh, darn it, I got a typo in my input deck. I mean, I think it's just much more productive. Actually, I think the ISV licensing stuff, it tends to be much cheaper to run a job running 6,000 cores than 100 jobs at 60 cores. So anyways, there's certainly pros and cons, and my message is, let's see if we can just bump it up a little bit.
All right. Thank you very much.
Yeah, thank you.